Oh, works. You actually did a very good job. That's pretty much how you pronounce my name. So yeah, I'm Simon Unge. I am Swedish. My colleague thought it was important to tell you that. I don't know why. But I live in San Francisco. I do work for, I have to be closer. I do work for Amazon MQ. More specifically, I work for RabbitMQ, or I work with RabbitMQ for the Amazon MQ team. So that's the hat I'm going to wear today, not my Amazon hat, but the RabbitMQ hat. And today I want to talk to you about how, is this working? It's not fine, by the way? Yeah. Okay, good. I want to talk to you of how our team is thinking about how to break the storage barriers of RabbitMQ streams and how to scale them beyond a local disk. Stand here. Firstly, a little quick primer for the ones out here who does not know what RabbitMQ streams are. They are an append-only log, one of the queue types of RabbitMQ with offset-based consumption. Think Kafka topics or a database transaction log. That means messages get written by multiple writers to in this context, to the tail of the log, to the very tip of the tail. And you have multiple consumers, and the consumers can start reading from the log at any point that they choose an offset, and they start reading from that offset towards the tail of the log, and eventually they end up at the tail. So keep that in mind, that there is a tail where writers are writing, and that's the place where the most consumers eventually, or all consumers, will end up there. So the majority of the reads will be at the tail of the log, but you can start it anywhere. And they read sequentially, right? They start somewhere, and then they just continue reading. Oh, yeah, I have this one. Yeah, and the difference here, of course, from traditional queues is like once you consume a message, it does not get deleted. It sticks around. So that means storage here becomes a matter of throughput and retention. So if you have a retention policy that says that you want to keep your data for 7 days, and you have a throughput of 10 megabytes per second, that ends up being 6 terabytes of data that you need to store. Keep that in mind as well for the rest of this talk. Streams are replicated, or they should be replicated if you want to have a durable system and distribute the load. So how this works in RabbitMQ is that you write to one node, we call that the leader, and you consume preferably from the other nodes that we call the replicas or the followers in order to just distribute the load, right? This is great for reliability. And it's good for load handling. Streams were designed, I think, for throughput in mind. And the throughput for RabbitMQ streams are kind of amazing. It's really, really fast. I'm not going to go into why and how it's fast. There are talks from previous talks for the RabbitMQ summits in the past, and blog posts written by the RabbitMQ maintainers that talk about how and why and all the cool features RabbitMQ streams has. That's not the topic of my talk today at all. But it is cool, so I would look it up if you have the time. But I don't think storage scalability was part of their focus. That was more of an infrastructure problem, so they pushed that to you, or the users of RabbitMQ. So one of the catches here, or like one of the consequences of this design, that you have a cluster of nodes, and each node can handle the consumers, means that all the nodes needs to have that data local as well. So they replicate the data. So if you have 6 terabytes of data in one node, that means totally you'll have 18 terabytes of data, right? Times the number of nodes that you have in your cluster. Because every node needs to have a full copy of the data set. So also keep that in mind for the rest of this talk. All right, let me tell you a little story. Let's do a little imaginary tale here. Let's say that you are responsible of an app called Ticket Champs, a ticketing platform where you sell tickets for shows, hockey games, soccer, football here, should be everywhere. And let's say that part of your system is a RabbitMQ cluster of 3 nodes, which handles your order streams. And you have 10 megabytes of throughput, like I said before, and you have 7 days of retention, so you end up having these 7 terabytes of data per stream. And the stream's handling your orders. They handle confirmation emails, payments, confirmations being sent out. You have an analytics platform that needs this data, and fraud detection or whatever. Like a bunch of different consumers that needs this data from the streams. Everything works good, humming along nicely. But then a disaster happens, and ignore the typo. Disaster. ABBA announces a show, and a one-day only show, one-night only show. And we're talking about the real deal here, like the actual members of ABBA will be on stage. It's not going to be holograms or anything like that. It's the 4 original members of ABBA will be on stage. Not sure if you know much about ABBA, but this is kind of a big deal. Millions, maybe billions of people want tickets, right? And they want them now. And for whatever reason, they chose your platform and they did not give you a heads up. So what happens? Well, traffic explodes. Your orders goes from 10 megabytes per second up to maybe 100 or hundreds of megabytes per second, right? Payment processing going through the roof, millions of confirmations, not millions, but a lot of confirmations need to be sent. Fraud detection system is struggling. Inventory system is struggling. Your nodes are at capacity. CPU is pegged, and the network is saturated. So what do? Well, you scale up, right? That's the natural solution to this problem. You just add more nodes. Like 3 nodes can't handle it, so we'll add 2 more nodes, and we'll have 5 nodes, and everything will be all dandy, right? Well, no. Because we have the problem here of replication. So for a node to be able to handle traffic, it needs a full copy of the data. And that takes time. 6 terabytes of data is a lot of data to replicate. So even if you have a fast connectivity between your nodes, say 1 gigabytes per second, if we do the math, it still ends up of being like 102 minutes or let's say 2 hours for replicating this stream. And you probably have more than one stream. But for this little experiment, let's say you just have one stream, right? So that means for 2 hours, your 3 nodes that are up and running won't get help from these other 2 nodes. So the system is struggling. Your customer gets all weird errors on their ends, like they tried to buy the ticket, it doesn't work. The tickets do sell out, but they sell out in an unorderly fashion, so you will end up having very angry customers and angry reviews, and you will have headlines in newspapers that you don't want. So we have a dream, and yeah, it's going to be about themed. So we have a dream in our little team to fix this, right? We want to scale out to go down from hours to just seconds, preferably. And our thought process, or our progress of thinking, was that we looked at what we have today, where we have local-only storage, 6 terabytes of data. That really doesn't really work in case of ABBA, right? We just saw that fail. Then we looked at traditional tiered storage, where you kind of solve that problem by having hot and cold data. So you have a certain amount of hot data, and older data, you ship it off to some kind of remote shared storage, and you call that cold data. But usually you have like a set amount of data that you store locally, like 50 gigabytes or something like that. And that kind of solves the issue a little bit. Like you do get scale out down from hours to probably minutes, but it's not good enough for ABBA tickets. We want this to be seconds, not even minutes is good enough, right? So we want to get to the lower point of this little graph here, where we minimize what gets replicated when we add a node. And we can't solve the replication speed, right? The 6 terabytes of data needs to be replicated on like the network is going to be the bottleneck here. Like we can't make that faster. There's no magic bullet to fix that. So instead, we need to solve what we replicate, and what we want to replicate is as little as possible. So instead of saying we replicate only 50 gigabytes of data, what if we only replicate the tail? If we aggressively upload everything else to remote storage, and in that way, when you add a new replica, all it has to do is get the tail from the other nodes of the cluster, say 50 megabytes or so, because, well, it no longer needs the full data, because the full data is already in remote storage, right? And yeah, compared to like traditional tier storage, we don't have to wait for data to age out or your disk to fill out. Like we immediately just archive it. So that's what we did, or that's what we're doing. And the way we're doing this, like we don't want to mess with RabbitMQ's sophisticated high throughput. So we didn't want to mess with the control plane at all. We didn't want to mess with how writes are done. We do not want to mess with how replication is done. We still want replication to happen because it needs to, and we don't want to mess with that at all because it's smart and clever, and don't mess with that. We don't want to mess with the reads, or we do want to mess with reads, but we don't want to mess with the read APIs. But we do want to mess with where the reads are coming from. So we also wanted this to be pluggable, right? We want to be able to fall back to the default behavior or add something different if you want that. So we introduced an abstraction layer where we have two behaviors or behaviors. Think interfaces in Java, but in the Erlang world, which is the language that this is built on, we call them behaviors. So two behaviors that we think that you need to implement: the abstract reader behavior, which it tells you how to read the data from somewhere, how from an offset a point in some file. Start shipping that to the consumer. And then we have the manifest abstract, which is where the data is. Like if it's if you come in with an offset, how do we find this message in a file or whatever kind of backend system you have. Like that's up to the manifest to tell you. And we wanted this to work as it does today if you don't want to use this. So the default behavior implements these two behaviors by doing what it does today. Like the manifest is the local disk, and reads just read from local data, local disk, just like it does today. Like we didn't touch that at all. Or you add a plugin, the remote storage plugin, which handles how to read, from where to read, and the archiving of the data. Yeah, I know. So let's talk about the write path here. And I want to emphasize that this is unchanged. I didn't talk about how writing works, but this is kind of very simplistically how it works. Like you have a publisher, it sends a message to RabbitMQ. You have a writer in RabbitMQ that writes that message to local disk, appends it to the log. You have replicas that take that message and does the same thing on their end. And then the message is considered committed when you have a quorum in your cluster. And that's it, like it's unchanged. That works just like it did before. Then, and I'm going to use the word asynchronously, even though I'm not entirely sure I should, we have a background process that uploads this data once it's committed to shared storage and update the manifest. So again, no impact on writes because we didn't mess with the writes at all. The reads, however, are a little bit different. The reader needs to know where the data is, and it knows that by looking at the manifest. So a consumer who does not care where the data is starts a reader. The reader tries to figure out where the data is. If it's on local disk, well, it just behaves like it did before. It reads the data from local disk very fast, no latency at all almost, right? Because it's just a local disk, and then it ships the data to the consumer. Or it's not on local disk, which means we archived it onto remote storage. And then we read it from there instead and ship it to the consumer. Now, since it's remote, there will be a little latency hit when we open the connection and set everything up, right? But we think, or we're fairly confident, that this small latency hit of 50 milliseconds or whatever it's going to end up being is all you'll see, because the throughput will be fast. And it will be fast or just as fast as reading from local disk. And the reason for this is because the data is sequential, right? You start reading from one point, and then you read forward in the history. So we know what the consumer is going to read next. So we can do some smart logic there and do prefetching and make sure that, yes, it's going to take a little hit in the beginning, but then it's going to be a throughput as you're used to. And of course, this is also completely transparent to the consumer. They don't care. They use the same APIs as before. Oop. So what does this mean? On the right or on your left, we have the old or the current setup where a new node joins, it tries to download, or it downloads all the data from the other nodes, 6 terabytes. And in 2 hours, it's ready. That's not acceptable for Bjorn and Benny. And then we have the new version where instead the new node joins and it only fetches the tail, 50 megabytes or so from the leader. And it's up and running in seconds, and the node is ready to start traffic. Because, yep, again, there's no full replication needed. Just fetch the tail, and everything is up and running, right? And it's a kind of a dramatic change here, right? So if we go back to our ABBA story, where ABBA announced their tour, and you saw the traffic spike, and we need to do something, and what we do is that we scale up, so we add 2 nodes. And now, in this new world, we get 2 nodes in seconds, and the concert sells out again, but it sells out smoothly. So you have happy customers, or maybe the customers who were there in time are happy. So the winner takes it all, and the winners are you and the customers, right? Now, we are currently building this, we and the Amazon MQ team, we're currently building the S3 plugin that implements this, the reader and the manifest part, and does the archiving of data up to S3, figures out the reads, figures out how to do this efficiently, right? It's open source, and it's work in progress, so please come and help us and look at it and come with ideas and yeah, contribute. But we'd also like to see you implement your own plugins for different backends, like Azure Blob Storage, or the Google Cloud Storage, or whatever, like your QNAP, NAS, or whatever you have. Now, I talked with one of the engineers from Cloud AMQP about this, and he said, can it be more generic? And yes, it should be able to be more generic. Like this could be what we're going. This is not what we're currently doing, but it would be cool if this is where we ended up, because I think that most of the logic in the reads and the archiving and the manifest will be very similar, depending on in regards of the backend. So we could probably make a cool cloud plugin where most of the logic is, and you just have to add small modules or small behaviors for authentication and basically how to do the puts and gets to those backends. This is where I call you for support to get involved. This is open source, like I said. We have a PR open for the abstraction layer that needs to go into RabbitMQ in the RabbitMQ Osiris library, which is the backend, streaming backend of RabbitMQ, PR 196. And then we have the S3 plugin that we're currently writing, that is working, but it's very much a work in progress. And like I said, it's all open source, so please get involved. Go and look at the PR for the abstraction and comment on it. Look at our S3 plugin design and comment on that. Try it out, create issues. Better yet, create PRs that fixes those issues, and come implement your own plugins. Share your use cases with us, and tell us if this abstraction level works or not. We think it does, but it would be great to get more input. And yeah, thank you for the music, and thank you for listening to my little story. The QR code should take you to the GitHub links and the Discord channel that's on the Discord RabbitMQ server. Questions? No? I'll be standing in the booth this afternoon. I don't know when, but at some point. So please come and talk to me if you have more detailed questions that you don't think you can ask me here. All right. Thank you.
Thank you very much. Thank you, Simon.